Hello, everyone.
Hello, hello. So welcome back to May Institute on Computation and Statistics for Mass Spectrometry and Proteomics. We are very happy that you could join us in this second week. We really wish you could be here in person and take advantage of the beautiful weather we have in Boston these weeks. But this is the second best. We are excited that you could join us in this online format. It is our first experience ever with the online format. So before we start, some logistics topics, especially if you are joining us for the first time. So at the bottom of your screen, you have a button chat. So this is the button you can use to talk to all the panelists and participants, but mostly for logistics questions. For example, if you cannot hear someone or you need a URL of some detail and so on. On the other hand, if you have questions regarding a actual presentation and the actual topic that is being discussed, then at the bottom you have a second button, a Q&A. And so this is a place to ask questions regarding the technical details. And please use this button because the speaker can monitor this and it allows us to, triage and manage the questions a little bit better. So this said, please do not hesitate to ask questions. And so now let's start. So the second week is focusing on R and R-based tools for mass spectrometry and proteomics. And the first presentation today talks about intermediate topics in R. And this session is led by Kylie Bemis. So let me introduce Kylie. Kylie is a lecturer in the Curie College of Computer Sciences at Northeastern University. She holds a PhD in statistics from Purdue. And she works extensively in developing R-based tools for imaging mass spectrometry. And later in the week, she will present her work on Cardinal. But today we were talking about topics in R. And so I'm passing on the virtual microphone to Kylie. Welcome, Kylie, to the May Institute. And thank you for joining us today.
Hello, everyone. So as I've just posted in the chat, please use the chat just for general logistical issues, or if I ask something such as, can everyone hear me? Things like that. If you have any questions about the actual course content or anything I'm going over, then ask those under the Q&A tab instead. Please save the Q&A for actual questions. Rather than just saying hi or things like that, leave that to the chat instead. We do have a kind of pseudo TA, Ting, who will be trying to help manage the questions as we work through some of the content. So I'd like to start just by giving everyone a brief poll that hopefully you should be seeing now, asking about your current R progress and experience. So this is aimed at intermediate or advanced R users. I'd like to get a little bit of an idea of where everyone is. So I'll just give everyone a moment to answer that poll now. So as I've described in, we do have there's a link to there should be a link on the website to a Google Drive or Google Docs that has the instructions for where to find all of the material for this course. And as I've stated there, I'm going to be skipping the first set of slides that I would have done if we would have met in person. That is a set of material that is basically going over things such as R Markdown, Git and GitHub, and some basic things like that. But just for time, we're going to skip those and jump right into the actual R content. So I'll be starting from the second set of slides on functions and functional programming. All right, so thank you everyone for answering the poll. Looks like most people here have either some R experience or are intermediate R users. So the course content will be focused on people who already have some R experience, have some intermediate experience, and I think a lot of the content will also be helpful for more advanced users. If you're a complete beginner, then unfortunately some of the topics covered might be a little bit advanced. So there's not much I can do about that. Unfortunately, we couldn't offer the beginners R course simply because it's very hard to do that remotely. But we'll try to be helpful as much as we can. And I'm going to go ahead and give you a second poll that I'll leave open for a little bit while we get started. So we have several topics that we'll be covering. I'm intending to skip the first one in R Markdown and Git and GitHub, so you can focus on the last four. I'm going to try to get through essentially as much as we can, but we only have 2 hours, so we're either going to have to rush some things or not get to some other things. So I'm going to launch a poll here, just fill in which of these topics are the most interesting to you, so we can try to spend a little bit more time on those. Meanwhile, I'm going to go ahead and get rid of this, and we will jump into our content on functions and functional programming, which is our first set of slides in the Google Doc. That is the second link to the slides. I also have these as R Markdown documents on the GitHub. All of these PDFs you can build yourself from the R Markdown documents using RStudio, as long as you have all of the necessary R packages installed. So some accompanying helpful material for this course are the Advanced R textbook by Hadley Wickham. This is freely available online at the link shown. And of course, the R language definition by the R core team itself. I won't be going through either of these in detail, but they're helpful resources if you want to further investigate some of the topics we'll be going over. So to start off, I'm going to kind of start from the very beginning. These first couple slides here are a little bit more theoretical than practical, but it helps to give us an understanding of how R actually works and how we should be thinking about programming in R. So this is from a quote from John Chambers, who is a statistician and the creator of the S language. For those of you who don't know, R is an open source version of the language S or S+, which came before R. And R is kind of the successor to S in that it's in the open source language for statistical computing that we use now. And so John Chambers, the inventor of the S language, had this to say about R. To understand computations in R, 2 slogans are helpful. Everything that exists is an object. Everything that happens is a function call. So I'm just going to take a few minutes to kind of go over each of these 2 slogans and what they actually mean for us when we're programming in R. So let's take a look at that first slogan. Everything that exists is an object. So let's consider a few very simple lines of code. So here I'm assigning 2 to X, assigning 3 to Y, and then I'm adding X and Y together. And if I switch over to RStudio and run these lines of code, and run these lines of code, well, X is 2 and Y is 3. So if I add those 2 together, I get 5, just as I would expect. The question now is, what is actually happening when I execute this code? So R is a really interesting and kind of cool language in that everything that exists is an object, and that means the code in R is an object itself that, if we wanted to, we can manipulate. So here, what I'm going to do is I'm going to use a function called quote, And what that does, if I go back to RStudio, I'm going to quote that expression that I just used, x plus y, and I'm going to quote it and assign that to an object called sexp. And if I look at this sexp variable, I can see it is just that code x plus y, the expression x plus y. And if I look at what type of object this variable sexp is, it is a language object. And so that means that goes to show that literally everything in R is an object. Even we can even treat the language, the code that we're writing itself, as an object. And that has a lot of really interesting implications for programming in R. And for example, that's why R is able to do some cool things, say, assign something new to X and Y. These are sequences of 1 to 10. And I'm going to plot these. And that is why, for example, when I plot y versus x here, and I create a plot of that, R is automatically able to detect the appropriate labels for the x and y axes. That goes back to the fact that the language and code that we write in R is something that can actually be manipulated as part of the language. So everything that exists in R is an object. We can manipulate this object, this language object. So for example, I have this sexp expression, x plus y. Let me go back and reevaluate this earlier expression, assigning 2 to x and 3 to y. So now I have this language expression, sexp. Let me increase the size here a little bit. And what I can do now is I can evaluate this expression. This is essentially what happens if I were to just type that expression in the console and hit enter. And that evaluates to 5 because x is 2 and y is 3. So when I evaluate that expression, it returns 5. But the really cool thing is I can manipulate this expression. I can assign, say I want to do multiplication instead of addition. I can assign into this expression the multiplication sign and replace that addition with a multiplication instead. And so now this sexp variable says x times y. And if I evaluate this, now I get 6 because 2 times 3 is 6. So that is what it means to say that everything that exists is an object. We can manipulate even the code in R itself. So one interesting question is when I assigned into this sexp variable to modify the plus sign into this multiplication sign, I assigned into the first element, kind of as if this were a list. And the reason that I did that is if I actually take a look into the structure of this language expression, I can turn it into a list with the as.list function. And what it shows me when I do that is this multiplication symbol actually comes first. And that's because this multiplication symbol is actually a function. So in R, when I write code that looks like this, assigning 2 to x, 3 to y, and then I do x plus y, this is actually the same as calling these different functions. This assignment function is assigning 2 to x, assigning 3 to y, and then using this addition function to sum x and y. And if I evaluate these two sequences of code, they are actually doing the exact same thing. They're just different ways of writing that code. This is called the prefix notation, which is the way that we normally evaluate functions where the name of the function comes first. And this is the infix notation where the function name actually comes between the two arguments to it. Normally, we would write it like this for things like assignment and addition. When we call functions normally, we will usually do that using this prefix notation. Yep. And this is further showing that everything that happens is a function call, because these assignment operators and the plus or addition sign are really just special functions. So that goes to the second slogan that John Chambers gave us, that everything that actually happens in R is a function call. If you have a question, go ahead and type it into the question the Q&A box. So as an example, suppose I wanted to do x plus 2, let's make it x plus 2 times y, or something like this. Well, we know due to the order of operations that this 2 times y will happen first, but if I wanted to make this more obvious, I can put that in parentheses. And normally these parentheses are, right now these parentheses are just to kind of show us what the order of operations here is more explicitly, but sometimes these parentheses are actually doing something, such as here, if I were to reverse the multiplication and addition, then I would need those parentheses. So that means these parentheses are doing something. Something is happening as a result of us using these parentheses in R. And if I go back to my slogans, everything that happens in R is a function call. So does that mean that the parentheses operator is a function call as well? And the answer is actually yes. The parentheses operator is also a function call in R. So if I wanted to, I could do something really sneaky and reassign the parentheses operator. So here I'm reassigning the parentheses operator, and now if I use a parentheses, they're secretly adding 1 to everything, which is of course something that you don't actually want to do, because you should never overwrite the parentheses operator. But it is something that is possible to do in R, because everything that happens is a function call. I just got rid of my own version of the parentheses operator, so everything's back to normal now. So everything that happens in R is a function call. So this leads us into talking about functions themselves. Let's see, there's a question in chat that I'll go ahead and address. Please, if you have questions, put them into the Q&A tab instead of the chat tab. It helps me keep track of them and alerts me a little bit more obviously. The question is actually, something that happens should come later than something that exists. Why R does it the other way around? Not entirely sure if I understand that. These two slogans are not necessarily implying an ordering two things. So I'm not quite sure if I understand that question fully. Maybe you can elaborate in the Q&A.
Kylie, just 2 questions. Maybe it's time to close the poll. And also, we don't see you. You don't have the video.
Okay. Is that better?
Yes.
All right, so just to remark on the results of the poll quickly, functions and functional programming was the most popular, so we'll be spending plenty of time on this section. Object-oriented programming was the second, which is the next set of slides we're going to go to anyway. So for the time being, we'll just continue here as planned. Ting, can you answer the question in Q&A about the materials? Okay, so functions in R. Functions in R are first-class citizens. What that means is that functions in R are objects like anything else that can be passed around and manipulated like any other object in R. That means I can do, let me define a function here. I'll call it add1. And this just adds 1 to something. And if I wanted to, I could assign this function to a new variable name. So I can pass functions around as objects like any other object in R. And that is what it means when we say functions are first-class citizens in R. Functions in R have three defining characteristics: a body. The body is essentially the code inside the function that actually gets executed when you call it. The formals is just the list of formal parameters that are used to call the function. And then lastly, an environment. We probably think about the body and formals of a function a lot when we're writing functions, but we don't often think about the environment of the function as much. But this is a very important part of the function because it defines where to find the function's variables when that function gets executed. So the body and formals we always provide when we're defining a function, but the environment is defined automatically by where you are when you define it. And we're going to see a little bit about what that actually means now. So let's start off by just defining a simple function. So this is going to be a function called add. If you never defined a function yourself in R, you do that by using the function keyword. And then the arguments to this function keyword become the formal parameters of the function. So here, if I call this function, keyword function, with parameters x and y, these x and y arguments then become the formal parameters of my add function. Whatever follows after this function, keyword, and the parentheses, then become the body of the function. So here I'm going to be assigning a function to a variable called add. And this is a function that is very simple. It just takes two parameters, x and y, and it adds them together, x plus y. And we can look at the different parts of a function by using these accessor functions in R. So the body accessor function will show us the body of a function. So if I call body on add, it will show me x plus y is the body for this. This is the code that actually gets evaluated when I call the function. The formals are x and y. I don't have any default values for these parameters, so they're just the names x and y. If I define some default values, then they would also show up here. And then lastly, there is an environment associated with this add function, and that is the global environment. Because I defined this function in the global environment, if you're not aware, the global environment is just it's the environment that you're kind of in by default when you're working with R at the console as a regular user. So all of your variables, all of your functions that you defined typically end up in the global environment. I can type ls to list the different variables that exist in my global environment right now. So I can see the previous variables that I had defined, as well as this new add function that I defined just now. So there's a question on when we would want to have braces here, such as this. So whenever you have a body of a function that is more than a single expression, that is when you would need to have braces. So here, for example, here I don't need the braces because x plus y is just a single expression. I can write this x plus y on one line. In R, the last evaluated expression in a function is what is returned by the function. So if you're familiar with other languages, you might think you need to return a value explicitly, but that is not the case in R. You can do it. There is a return function that will return a value, but by default, the value of the last evaluated expression is what will be returned by that function. So here, for example, add. If I add 2 and 2, that gives me 4. Add 2 and 3, that gives me 5. And so I don't need these curly braces if I can fit my function on one line. However, say I want to make this, say I want to do some additional processing inside of my function. I'm just going to create additional temporary variables that isn't needed in this case. But if I had a function that took up more than one line, then I would need to wrap the body of that function inside these curly braces so that this is all part of the same function. If I can fit everything on one line, then I don't need to do that. Let's see, there's another question. How many types of environments are there in R? So there aren't really types of environments, but there are essentially as many environments as there need to be in R. I'll go into more detail on exactly when environments get created and destroyed in a moment, but by default, there is always the global environment that you have access to when you start R. This is where your user workspace. In addition to this, there are a few other environments to potentially be aware of. There is the base environment, that is where all of the functions and variables from R's base package are defined. So things like the plus operator would be defined in this base environment. On top of that, each package that you load will also have its own environment. And we'll see a few other places that environments get created and destroyed. So I'll go into a little bit more detail on that when we talk about how functions are evaluated. Another question, if for some reason one wants to return a value other than the last calculated expression, does using the return function override the default action? And yes, that is exactly the case. So if I want to return something early, so maybe I have a function that does a lot of heavy computing, but if some condition is true early on, then I can return some other value. So I can always return something explicitly by using this return function. And so here in this case, this function will return 1 before it ever gets to the rest of this code. And if R gets to the end of the function's body without returning anything else, then it will return the value of the last evaluated expression. But you can use this return function to return things earlier than that if you want. Okay. So talked about the body, the formals, and the environment. So before moving on, I want to point out that there is one kind of exception to the two functions always having these 3 parts to them, and that are so-called primitive functions. These are functions that are defined only by the R core team, and these are essentially functions that immediately call C code upon being called. So plus is an example of a primitive function. When you call plus, it immediately goes into C code without doing any other evaluation in R itself. Primitive functions only exist in the base R package, and they can only be created by the R core team. So we're not going to talk about these further beyond pointing out that they exist. So they are kind of a slight exception to this rule. All right, so defining a function in R. We just went over it. When you define a function, you use this function keyword. The arguments you provide to this function keyword then become the formal parameters of the function. Whatever expression you give after that become the body of that function. If that body needs to go over a single line, then you surround it in curly braces. And whatever environment you're currently in becomes the environment for the function. Typically, as a user, you'll be in the global environment, so most of the time, the environment for the function will be the global environment. Question, can you say the environment defines the scope of a variable? And the answer is yes, kind of. We'll talk more about scoping in just a moment when we talk about exactly how a function is evaluated, but an environment is part of what defines the scope of a variable. And we talked about returning things explicitly with the return function. All right, so before we keep going, before we move on, I'm just going to give you a quick small exercise that if you happen to have R open, you can do on your own. Just give maybe a minute if you want to do this, but write a function that replaces all of the missing values, all the NAs in a numeric vector with the median value of that vector. So go ahead and do that. A question in Q&A is about the ... in functions. I will get to that a few slides from now. So we'll be getting to the ... soon. So there are lots of ways to potentially solve this if you want to replace all of the missing values in a numeric vector with the median. Wait just a moment as you think about how you would do this, even if you're not actually writing the code. So one way that you could have done this is something like this. So this is one possible version of this function. I called it impute_NA. It's a function that takes one argument x, which is assumed to be a numeric vector. And the way I chose to solve this is to use this if-else function. What this if-else function does is, this is a very useful little function if you've never used it. But if-else is a vectorized version of if-else that you give a vector, a logical vector of trues and falses, and then two other vectors. And if-else will return the corresponding elements from those following two vectors, depending on whether the corresponding element of the first vector is true or false. So for example, here, I'm giving if-else the vector true, false. Wherever this vector is true, it will return the corresponding element of the second argument. So it'll return a 1 here. Wherever this is false, it will return the corresponding element of the third argument to if-else, so this other vector. So in this case, it will return b here. So if I evaluate this, the first element is true, so it will return 1. The second element is false, so the second element will be b, and it will return to me a vector of that form. In this case, the vector ends up as a character vector because I have both numerics and strings. The strings are more complex, so the strings win in terms of coercion, and the result is a string with 1 and b. So the way that this if-else works in this impute_NA function is I'm going to check is_NA. Is_NA is also vectorized, so it will return to me a vector of trues and falses. That will be true wherever x is missing, false otherwise. And wherever x is missing, I'm going to return the median of x, calculated by removing missing values. And wherever is_NA is false, so wherever x is not missing, I will just return the original value of x.
Hi, Kelly. I think we have a question about the code, single quote or double quote.
Yes, so is single quote same as double quotes all through in R? For the most part, yes. There may be some exceptions somewhere, but generally speaking, single quotes and double quotes are the same. So if you want to have a quote inside of a string, then you just use whichever quote you didn't use to surround the whole thing. So here, if I have hello world, this will be the same whether I use single or double quotes. And then if I want to have a string, a quote inside of the string, I just use whichever quotes I did not use to quote the whole string. So both of these do the same thing. Question is, does the median calculation here run more than once in this function? Which is a really good question. And the answer is no. This median function should only run once. The reason for that is actually slightly complicated and gets into things called promises. But the shorter answer is this will only run once. I'm passing it as an argument to the if-else function. So when if-else goes looking for the value of the second argument to if-else, it will see this expression, evaluate it once, and then use the result of that expression whenever it needs to. Now the question, what if we want to put a function in place of the median? I'm going to talk about that in just a moment. So that'll be in a couple slides from now. All right, so we wrote this function. I'm going to quickly show that it works. Let me execute it here.
Hi, Kelly. I think the bottom of your RStudio is somehow covered by the Zoom. Could you move it? Yes.
All right. All right, so we defined input NA. And let me come up with a little example here. So here is my X. If I input NA on X, it will replace these NAs with the median, which in this case is 3. All right, so that looks like it works. So good job. We wrote a function that imputes NAs with the median value. So why did we write that as a function? It seems like we could, if we ever wanted to do that, we could just use this, replace that impute NA with this same expression. It's not much coding to do that. So why write this as a function in the first place? So take a moment to think about why you would want to write your own function to do something like this, or just general reasons for why you might want to write a function. So some reasons that you might want to write a function are, the first and foremost, to avoid duplication. Copying and pasting your own code is generally bad. You don't want to have the same code repeated multiple times throughout a script. That introduces the possibility of making errors. It makes it difficult to change later. So if you want to change a single variable or the name of a variable somewhere, if you copy pasted the same code, that means you have to fix it many more places wherever you copied and pasted it. So it's really difficult to maintain. Someone said reusability, exactly. So you write a function to avoid duplication and to be able to reuse that common workflow, that common functionality without needing to copy and paste it. And you also might want to share that new functionality with other people. So having writing something as a function makes it really easy to share that functionality, that whatever that function is doing, with other people, so that they can just call that function without having to copy and paste a huge chunk of code. One quick question, can the function that we just wrote also apply to a matrix? It will correctly replace the missing values in a matrix, but I'm not sure if it preserves the dimensions or not. So let me check real quick. So here is X as a matrix. Let me put a missing value into it. Take a moment to guess whether you think the result of this will be a matrix or not. It does preserve the dimensions, so it seems like if-else does preserve the dimensions, so this function does also work for a matrix. Question, what are the characteristics of a vectorized function as opposed to a non-vectorized function? A vectorized function is essentially anything that can take a vector and applies the same thing to every element of that vector, or anything that you can pass a vector, to it and have the operation apply to everything in that vector in a way that makes sense to avoid iteration. Essentially, if it lets you avoid writing a for loop or using one of the apply functions that we'll be talking about, that means that that is vectorized. So as, let me think of another example that we can use here. The addition operator, let's say x is 1 through 10, y is 11 through 20. So x plus y is, or the addition operator is vectorized. If the addition operator was not vectorized, we could only ever apply it to scalars. But since the addition operator is vectorized, that means we can add two vectors together, and the addition happens to every single element of those two vectors. So that's kind of what we mean when we say that something is vectorized. It means that we can give a vector directly to a function and avoid iterating ourselves with a for loop or an apply function. Is if-else a primitive function in R? It is not. So an easy way to find out is to just check the code of a function. You can do that just by typing the name of the function in the console and hitting enter. Here I can see this is the code for the if-else function. It's all written in R, so this is not a primitive function. If it were a primitive function, such as sum, then I would just see this dot primitive called a primitive. All right. So as an example of why we would want to write functions, it's just an example of two kinds of code snippets. In the first part, we're just copying and pasting the same pattern that we use in our input NA function to impute the missing values for each column of what I'm assuming to be some kind of data frame. So this is the first way that you might go about imputing all of the columns of a data frame versus using our impute NA function. And if I were to ask you which is better, I think the second version here is definitely better. There is still a good amount of duplication in the second version because we're calling this impute NA function multiple times for each of these different columns in the data frame. So we can still further improve on this and reduce the duplication here as well, but we'll get to that a little bit later on. So suppose we want to write a more flexible version of this function and let the user specify whether they want to impute with the mean or the median. So this is starting to approach an earlier question of what if we wanted to have something other than the median in here. So this is the kind of the first version of us trying to do this. We're going to go through a couple of iterations of this. So here, one way that we could do that, a very simple way, is to just have a second parameter called method, and just have, let me go ahead and move the slides a little bit like that, is to have a second parameter called method, and this method might be the mean or the median, and a string of the mean or median, and we're going to check inside our impute NA2 function whether the method that the user wants is the median or the mean, and depending on which of these we get, we'll use the corresponding function. So here is a version of our function that does this. So this is kind of the simplest version, kind of the first version that you might try if you wanted to allow some kind of user customization here. So here we're imputing with the median, but I could also change this and impute with the mean instead. But the problem here now is that the user always has to provide a second, an extra argument. So let's think about some ways that we might avoid forcing the user to always provide the second argument. Meanwhile, there's another question in the Q&A. When two vectors are added, is there an automatic size check? What happens if they are different sizes or dimensions? And so when you have vectors of different sizes, let me do x is 1 through 10, y is 11 through 15. So in R, R has something called recycling, which means that if you try to add or do pretty much anything with two vectors that are of different lengths, then the shorter one will be automatically recycled to the length of the longer one. So here, x plus y, where x is 1 through 10, y is 11 through 15. X plus y in this case is essentially the same as doing x plus y, y. So internally, something like this is what's happening, or more accurately, this is what is happening, where the shorter of the two vectors is recycled to be the length of the longer vectors. This is in some cases very useful. So for example, when you're multiplying a vector by a scalar, the scalar is automatically recycled to be the length of the full vector. So we can do something like 2 times x or 2 plus x, and the 2 gets recycled to be the full length of the vector. But there are times when this can end up a little weird. So suppose I have y is 1 through 3. Now, if I add x to y, I will get a warning message because the longer object is not a multiple. The length of the longer object is not a multiple of the shorter object length. So if it can't do this replication neatly, it will give you a warning about this. So this is something that's kind of a double-edged sword in R. It's very useful for situations like multiplying by a scalar, but it can kind of bite you if you're not aware that it's happening. And the same is generally true when doing operations on matrices or arrays. Let's see, so when writing a function like this, how can I know where to put the braces? So these braces are essentially like grouping. So when I am writing this function, my function is more than one line. So everything in this function has to be surrounded by one set of braces. When you are doing an if-else statement, generally the what is following the if or the else is also surrounded by braces. So after this if, excuse me, the body of this if has a brace around it, and then the body of the else if also has a brace around it. Question, what does impute NA2 return if user does not put a method to be mean or median? That is a good question. So if we just execute impute NA2 without providing a second argument, we'll get an error because the second argument is missing with no default value. And that's what we're going to fix in the next version of this function. We're going to provide a default value so that we have something to fall back on if a user doesn't provide a second argument. So what if we want to have a different function, such as the mode? This is, again, something we'll be doing in the next version of this function so that we can make it more flexible. Can we return both median and mean at the same time? So this one's a little bit more complicated. This one isn't a straightforward extension of the same function, I would say, because in all versions of this function, we're going to be returning a vector of the same length as the original vector. If we wanted to return different versions of the vector, we would have to put those all into a list, is the way that we'd return multiple of these at the same time, or put them as columns of a matrix or something like that. So that is the way that we would return multiple versions of our imputation at the same time. I would say that usually that's not really something we would want to do, and we would want the user to just call this function multiple times if they wanted to do something like that. Question, when do we use this C function? So this is just a function for concatenating things together to make a vector or anything vector-like. So I'm just using the C function to make a vector of numbers in this case, but we can also use it to make a character vector of letters or something like that. It's a really simple function that's a primitive function that combines vectors, or in this case, scalars or length 1 vectors into a vector that is the combination of them. What is the difference between the usage of if-else and else-if? So if-else, the function is a vectorized function. So it takes as input a vector and returns a vector. This is different from the control flow of if, else, and else-if, because if and else-if are looking for conditions that evaluate different code. They branch to different code. So this if, else, these are control flow that decide what code you want to execute. Whereas this if-else function is more of a convenient way of returning a vector that is a combination of 2 different vectors based on some condition. Question is, what if this rep_len function only gave a warning message? Can we force it to compute anyway? So generally speaking, when you're relying on this recycling thing, so 1 through 3 plus 1 through 5, usually this will just be a warning message. So it will usually compute anyway. You'll just get this warning message. If you wanted to turn it into an error, there are ways to do that, but generally this kind of thing will compute anyway, so you don't have to worry about it throwing an error. But it is generally something to be very aware of, since it can easily lead to mistakes. So it is good that it throws a warning in this case. Question, what does the equals do? So this is a check for equality. If I want to check if 2 things are equal, I use the equals operator. So here, I don't have anything assigned to it. So here I'm checking if the method provided is equal to the string median. It is. Then I'm checking if it is equal to mean, which is false. So this is just checking for equality, the equals operator, not to be confused with the equals operator. Is there a way to not write too many else if you have 3 or more options for a method? Yes, and depending on exactly the way that you want to do that, there may be different ways to best write a function if you have multiple branches like this. And we'll take a look at least a couple of options for that in just a moment. Okay, moving on. So here, the issue was we wrote a version of this function that imputes with either the mean or the median, but the user always has to provide an extra argument. So what if we want to make it so that there is a default? The way that we can do this is just to provide a default value. So when we're defining our function, we can just provide a default value for the formals if we want to. And so we can just set the default for this method parameter will be equal to median. So that means if the user doesn't provide a value for this method argument, then it will automatically use the median. So here, I'm going to run this. And now if I call this impute NA3 without a second argument, it will automatically use the median, but I can change it to use the mean if I really want to. So that seems okay, but the user doesn't really know what the possible options are here unless they go look at the documentation. Also, we would have to make sure to fully specify all of the possible options in our if and else if, and there's no easy way to partially match what the method might be. So a slight improvement in this case is to provide all of the possible options in the function signature in the formal arguments. So here we're providing the default value as all of the possible options. And then inside of this function, we're using this match.arg function. And this is a helper function that we generally use inside of a function to match what was actually provided to one of the possible options. And it will throw an error if the user didn't provide one of the possible options. And by default, if the user didn't provide any options, it will give the first option. So that means here we're setting the default of method to a character vector with the options median and mean. We're using match arg to determine what was actually selected for method. And if method wasn't passed by the user, then it will default to the first option, which is median. So to show that, I'll run this. And so here, if I run this without any additional arguments, match.arg will default to the first option, which is median here. I can still choose the mean instead. And also, if I provide an option that isn't supported, say sum, then match.arg will automatically throw an error in that case and say that the options only median and mean are supported here. Okay, so that is all well and good, but what if we wanted to be even more flexible? So kind of the ultimate in flexibility is to take advantage of R's first-class functions and allow passing a function itself as the argument. So here, instead of a string such as mean or median, we're going to let the user to actually pass a function that will be used to determine the value to impute. So here we're going to rename our second argument to fun, and the default value, we're still going to provide a default value, but now it's going to be the median function as a function rather than as a string. So in this version, we're going to use this other helper function, match.fun, which guarantees that this fun argument is going to be an actual function. If they provide a string, match.fun will try to find the corresponding function with that name. If they provided a function, then everything's fine. If something other than a function or the name of the function was provided, then match.fun will throw an error. So in this case, let me run this. The default is to use the median function. So impute NA5 by default will impute with the median. I can now pass a different function for calculating what to impute. So here I can pass the mean function to do that. And using this match.fun function also means that I can provide the name of a function as a string, and match.fun will do its best to find a function with that corresponding name. So those are a few different ways that we might approach writing this particular function and offering different options to the users. So when you're trying to write good functions, there are some things that you should try to aim for. The first one of this is that it's good if the function is obviously correct. That when you read the body of the function, when you read the code, it is clearly doing what it is actually supposed to do. This is the ideal case. Sometimes the code gets complicated and it is less obviously correct, but ideally a function should be obviously correct. Speed is another thing to think about. But most cases, it is best to write a function that works correctly first and only optimize later if speed becomes a problem. You should generally avoid premature optimization until you can benchmark it and find out that speed is actually an issue. You should generally try to write more specific or simple functions than more general and complex ones, although sometimes more complex functions are necessary. But generally, the best functions are functions that do one single thing and do that one thing well. You might consider how concise or short your function code is versus being more verbose and easy to understand. When you're writing a function, you have to think about things like the names of variables, how clear it is what is happening. And so these are all things to keep in mind. I think it's generally better to write a little bit lengthier code that is easier to understand rather than to try to do something clever that might be harder to understand. And always the hardest part about writing a function is providing a useful name. Lots of times if you've worked with R or really any programming language and you're looking for a function that does something, but it's named something unintuitive, it can be difficult to find that function. So trying to come up with a good descriptive name for a function can be really hard, especially when you still want it to be relatively short and easy to type. So spend a lot of time thinking about what the most useful name for your function is. Question, is fun a default setting or can we use another name like funny? So here, the names of your formal parameters in a function can be anything you want. I changed it from method to fun to clarify to users of this function that the argument should be a function rather than just a string, although a string that provides the name of a function will also work in most cases. But fun could be anything. So if I wanted to change it to funny, as in the question, that would also work. So this will still work. But the arguments, the names of the parameters here can be the names of the parameters here can be anything we want them to be. In addition to thinking about function names, though, that is a good point. In addition to thinking about function names, you should also think about the names of your arguments and what they imply about the possible values that a user can provide for those. So here I chose the name fun because the user needs to pass a function. Is it possible to replace NAs using values from a normal distribution curve? So we can decide how the imputed values are calculated however you want. You could certainly write some code in here that uses something from a normal distribution, or write a function that calculates things from a normal distribution and provide that as a function here. I'm not going to go into any details or things like that on how to do that, but you could certainly come up with a function that does whatever you want. So this function could be a user-defined function that calculates what the values to impute in any way that you want. Okay, so next thing I want to talk about is anonymous functions. So this is something that's really useful in R, is this kind of construct, although sometimes you might not do it exactly like this. But a useful thing in R is that you don't always have to name your functions. You can actually just call functions without giving them a name or pass what are called anonymous functions. So these are functions that haven't been assigned to a variable name. So here I'm passing a function that I've created in place that takes an argument x, which I'm assuming to be a vector, and an argument called na.rm that defaults to true. And what this function does is it sums up x and divides that sum by the length of x. And if you think about it for a moment, you should recognize this as calculating the mean. So this is just an anonymous function that calculates the mean of x after removing missing values. So I could just pass the actual mean function, but this is just to demonstrate that you can, R does allow you to pass anonymous functions like this without having to define it formally and give it a variable name first. So this here will also work. This is just some more examples on how this works. So we don't have to assign a function to a variable to use it. This is a perfectly valid function all on its own, and I can call it just like I would a normal function. This is called an anonymous function, and these are something that you'll most often write if you want to apply kind of a quick and dirty custom function to functions like lapply and sapply that we'll talk a little bit more about later. All right, so I'm gonna go back to our impute NA5 version of this function, and you might have noticed in this version where I was passing this anonymous function, I made sure that this function takes the na.rm argument just like the actual mean function does. Remember, this just removes the missing values before calculating the mean. And so if I were to define this function without that na.rm argument, so like this, and try to pass this anonymous function to our impute na function, well, I actually get an error. And it says their unused argument na.rm equals true. So why did this happen? So to understand this, let's go back to our definition of impute NA. So this is our definition of impute NA. It looks like it's still defined with this funny argument name. But if I look at this definition of impute NA, I'm eventually calling the user supplied function with this argument na.rm equals true, which makes sense because most of the reasonable functions that I might pass, like mean or median, have an na.rm argument. But that means when I pass a function that doesn't have such an argument, I get an error because suddenly this function doesn't know what to do with this additional argument na.rm equals true. So whatever function we pass to this impute na function has to accept na.rm as one of its arguments. But what if we don't know exactly what arguments a function inside of another function might accept, and we want to allow the user to pass any arguments along to it? So this is where that ... operator or argument that someone asked about earlier comes in. So what this ... argument does is it says this function now takes any possible number of arguments. I could call this function impute na6 with any number of arguments that I want. Any arguments beyond these first two have to be named, but whatever these arguments are, I'm going to pass them along wherever I see this ... again. So when I see this ... in here, when I'm calling this user supplied function, I'm passing along this ... And that means whatever arguments are additional arguments are provided up here are then passed along to the user supplied function down here. So this ... is a way of passing along arguments that your function might not know what to do with to some other function that your function is eventually calling. This is used a lot with functions that do some kind of plotting. Because plotting, the function for plotting things tends to take a lot of arguments. And so a lot of those arguments might get passed along to the function that actually plots things as this kind of ... operator. So if I define impute na6 here, I can call it now like this. But kind of the drawback in this case is that if I don't pass on this na.rm, now the missing values actually stay, so our function doesn't quite do what it wants to. So in this case, this isn't an elegant solution here because now the user has to manually pass this na.rm argument. But that is just to show you what this ... is doing. It is taking any additional arguments that I provide, in this case na.rm, and passing them along, in this case, to the median function, when it is finally called inside of my impute NA function. All right. So here, what if we want to allow the user to pass some kind of constant value to use for the imputation, but we want to fall back on using the median otherwise? So I'm going to talk about lazy evaluation now. First, there's a question. So question is, in essence, the additional argument must correspond to an argument in the internal function. So whatever additional arguments we pass via this ... should correspond to arguments in whatever function we're passing the ... to. That doesn't necessarily need to be the case because, and if a function has a ... as part of its signature, extra arguments will be ignored. So that means here, this na.rm gets passed along to the median function. But since median takes ... if I pass additional arguments along to it, median won't complain, although I believe they will actually become part of the calculation of the median, just because of how the median function works. So whatever additional arguments will get passed to the internal function through this ... that function either needs to deal with those arguments, or if ... is part of its signature, then it might just be able to silently ignore them. Can we try other arguments here other than na.rm? So median only takes x na. So median takes only x na.rm and this ... arguments. Median, the way it is defined, I think any arguments passed via this ... will just become, well, maybe it does simply ignore them. Oh, those are being passed as the na.rm. Okay, so in the case of median, it looks like the median function is automatically ignoring any additional arguments it gets beyond x and na.rm. So if we wanted to, we could pass any additional arguments that we wanted to. And if median did take other arguments besides these, we could pass them along here. If we provided a different function besides median, we could provide any additional arguments that that function happened to take as well. So this works for any arguments. Why would you want to define an anonymous function? It seems like that would lead to confusion and ambiguity. So the reason that we might use anonymous functions like this is lots of times, especially if you're using the apply and lapply functions that we'll talk a little about later, you might want to provide a function that's really only going to be used once. And in which case, actually assigning it to a variable name isn't going to make things much clearer, and then you would have to decide what to name the function. So when a function is only really going to be used once, then there might be no real need to assign it to a variable if you're only going to use it that one time. So in those situations, it kind of makes things a little bit neater or tidier to just use an anonymous function. So for example, say I had a list of vectors. So this is kind of previewing of things to come. Suppose I have a list of vectors and I just want to add 1 to all of these vectors. Or yeah, suppose I would just want to add 1 to all of these vectors. Well, a simple way to do that is to use lapply and just pass an anonymous function that adds 1 to everything. And in this case, I could, if I wanted to, define a function that all it does is add 1, and then pass that function. But in most cases where you would be doing this kind of thing, hopefully you're defining a function that's simple enough that it's still clear what you're doing. And so assigning it to a variable name doesn't really change anything. So that's kind of why you would want to use anonymous functions, and where you would want to do it is where it's really only going to be used once. So a question on the difference between apply and lapply, we'll get to that in a little bit. We'll be talking about those shortly. Okay, so lazy evaluation. So here, the idea is we want to allow a user to pass a constant value for the imputation rather than a function, but fall back on using the mean otherwise. So suppose instead of replacing the NAs with an imputed value, maybe we want to replace them with an error code or some other kind of special missing value code or something like that. So the example here is I'm replacing the missing values with -100 for maybe that's a special missing value code that my domain uses or something like that. So what we can do here is I'm going to create a default value for my, I'm going to define a new impute NA. Now I'm going to name the second argument value because I'm going to allow passing some sort of constant to be using for the imputation. And I'm going to assign this a default value called default value. And inside of my function, inside the body, I'm going to check if this argument is missing. So this missing function is a special function that you can really only use inside of functions that checks if a user has passed a value for one of your parameters. So if the user didn't provide a value for value, then missing here will be true. And if the user didn't provide a value for my value parameter, I'm going to assign median to default value here. And so now I'm going to do my Ifelse, and wherever x is NA, I'm going to replace it with value. Otherwise, I'm going to replace it with x. The really curious thing here is this default value. So first I'm going to show that this works. So here, suppose I'm replacing all the missing values with some error code -100. And if I don't provide a constant value to replace the missing values with, it's just going to default to the median. So the kind of weird thing here is that default value isn't defined when I provide it as the default value. And I'm only providing a value for this if this parameter is missing. And that's because of something called lazy evaluation. So value doesn't actually need to be defined as anything until our R actually tries to access it. So that means even though default value is undefined, it's only going to be needed if the user doesn't provide some other value for this value parameter. And at that point, if the user didn't provide anything, well, I've defined default value as the median. And so when I get to my Ifelse and R tries to find the value of this value variable, it's going to look for the value of default value. And at that point, I have defined it as the median of x. So this is called lazy evaluation, where R doesn't bind values to parameters until it actually needs them. So in this, we're using missing to check whether a user provided a value for this parameter. And if they didn't, we just assign a value to this default value. This is called lazy evaluation, where R doesn't need to know the value of this parameter until it's actually used, which doesn't happen until here. Missing is a special function that doesn't actually care about the value. It just checks whether the user provided something or not. So this is something that's kind of cool that lets us provide default parameter values that actually get defined inside of the function. And that's something that is kind of cool just because it lets us do neat tricks like this. And by neat tricks, I mean, it's a little bit obfuscated, but what it lets us do is it lets us keep the function signature clean and use some kind of internal logic inside of our function to provide a sensible default value here. So that we don't actually have to write the code to figuring out what this default value should be inside of the formals. Question, could one use value instead of default value under if? So the question is, in this if statement, could we replace this value with default value? And the answer is no. Missing is a special function that only makes sense when applied to the formal parameters of a function. So the formals of impute NA7 are x and value. Value happens to have a default called default value, but value is the name of the actual formal parameter. So I have to apply missing to value itself rather than its default value. Could we do this instead? Yes, this would also work. We could do it like this. Kind of the reason I showed it like this is to demonstrate that how we can do this using lazy evaluation. Technically, in this case, this is a really simple case, so you could do it just like this instead, and this just check if value is missing, assign a value to it y. So in this case, the lazy evaluation wasn't actually necessary, but in more complicated cases, it might make more sense. All right, so now I'm going to talk about scoping. Actually, just a second. So I am running low on battery, even though I am plugged in. So everyone give me a moment to figure out my power situation. I think my power strip is off. So I'm going to check that for one moment. Okay, sorry about that. Question was, default value might have been necessary as we couldn't call the function without a second argument then. So in this case, this case is simple enough that we don't need to provide a default value. This will actually still work in this case, and that's because of this missing argument. Missing doesn't care about the value of the parameter, in this case, the value of value. So we can, by the time that we actually need the value of the parameter, we've assigned the median to it. So in this case, we don't actually need the default value default there. In some cases, in other cases, more complicated cases, you might need it. Okay, so how does R actually find the value for default value in this case? Or more generally speaking, how does R know where to find the value of any of the variables inside of its functions? So now we're going to talk quickly about lexical scoping. And this is how a function finds the values for the variables in its body. So I'm going to make a simple function called add1 that just takes x and adds 1 to it. This makes sense. This is a pretty simple function that makes sense with everything that we've learned so far. But now I'm going to make another function called add_y. This function takes one parameter x and adds y to it. The strange thing is y is not an argument, is not a parameter for this function. So if I add y to something, say add y to 1, well, what do you know? In this case, it works. Happens to be because I have a y in my global environment. Let me remove that y. Now I'm going to add y to 1 and take a moment, think about what might happen. I get an error. Y is not found. So what is happening here? So functions always capture the environment in which they were created and have access to all variables in that environment. So when I defined add_y, I defined it in the global environment. The global environment. And so that means add_y has access to all of the variables in my global environment. So now if I assign 1 to y, all of a sudden my add_y function will work again, because now it can find y in the global environment. And that means we can define functions like this that depend on variables that are not part of their formal parameters. Why might we want to do something like this? As an example of why we might want to do something like this, suppose we want to write a function that actually returns a function. This is something called a functional, when you have a function that either returns another function or takes a function as an argument. So here I have a function, I'm going to call it add_val, that takes some argument val and returns a function that takes an argument x and adds val to x. So add_val is kind of like a function factory in that it will return to me new functions that just add whatever argument I pass to val to their own argument. So I'm going to create a function called add10 as a result of calling add_val of 10. So add10 is a new function, and I can call add10 to anything, and it'll add 10 to it. And the strange thing is that if I look at the body of this add10 function, I can still see a val in there. So I'm just adding val to something. So somehow this val is sticking around even after I've long since executed my original add_val function. So to understand this, what exactly happens when we call a function in R? The following things happen. First, a new temporary environment is created. So we talked a little bit about environments. By default, you're in the global environment. But new environments can also be created, and in fact, they're created all the time whenever you call a function. R will automatically create a new function when you call a function. Any of the formal arguments of that function are assigned into that new environment that was just created. The temporary environment's parent environment, also sometimes called the enclosing environment, is the function's environment. So that means when I call let's say add_y. When I call add_y, the first thing R does is create a new temporary environment. It assigns x, the value of x, into that environment. And the parent of that environment is the environment of add_y, which in this case is the global environment. Now, whenever a variable name is encountered in the body of my function, R will search first that current environment, so the temporary environment that was created, then its parent environment, which happens to be the function's environment, then its parent environment, and so on until a variable is found. So that means with add y, R first looks in the temporary environment that gets created when we call add y. It doesn't find a y there, so it goes up one level, looks in the global environment, it finds a y and binds that value to the y in that environment. So that is what is happening with this add val. The difference is the function that I return from add val has a different environment than the global environment. It has the environment of the it has the temporary environment that was created when we called add 10 has the temporary environment that was created when we called add val. So when we evaluate this add val function, it creates a temporary environment, assigns 10 to val, and returns a new function. And the environment of this new function is that temporary environment that was created where val has the value of 10 assigned to it. And so our add 10 function has this environment. And if I wanted to, I can look into this environment. Val exists in this environment. And on top of that, I can look at val, and I can see that it has the value of 10. And so that is where this val is. The function add 10 is carrying with it the environment from when we first called add val. When a function is stored together with its environment like this, it's what we call a closure. And this is something that's really useful. For example, there is a function called approx_fun, where you give approx_fun an x and y, and approx_fun returns a new function that does interpolation of y given values of x. So that's something useful if you want to pass that function along to do other things to it rather than just get the approximation right away. All right, let me see how much left we have here. All right, okay, kind of the last thing in this section before we try to do a crash course on object-oriented programming is these apply functions. So I've been referring to these for a while now. In R, these apply functions are used very frequently. And in R, these are kind of what we tend to use in R rather than for loops. So these apply functions just let us apply some function over each element of a vector. lapply will always return its result as a list. sapply is the same thing as lapply, but then tries to simplify its result. And vapply is a variant of lapply also that tries to simplify its result according to some template. So what does that actually look like? So lapply always returns a list, and what lapply does is we give it a list and a function, and lapply applies that function to each element of the list. So here we have a list X with 3 elements that happen to be vectors. I'm going to sum each of these vectors by doing lapply on X and giving it the sum function to sum each of the vectors corresponding to each of the elements of X. So sum is passed, applied to each of the elements of this list. I could do the same thing with, say, the mean or the median, and so on. sapply is just a variant of lapply that does the exact same thing, but then it tries to simplify its result into some kind of vector, matrix, or array. So here it simplifies the results into a numeric vector. vapply is a variant of sapply that does the same thing, but it simplifies the result according to some kind of user-supplied template. So in this case, the result of sum is going to be a length 1 numeric vector. So I supply what the result of sum will look like, a length 1 numeric to vapply, and that means it's able to do that simplification more efficiently than sapply does. Because as vapply knows beforehand that each result of sum is going to be a length 1 numeric vector, so the final result is going to be a length 3 numeric vector. So it's able to allocate that beforehand and do that simplification more easily than sapply, that first produces the list that lapply does and then tries to simplify it just by looking at what the return value was and figuring out if it's possible to simplify it. Right, so an example that we had earlier was we were applying impute NA to all of the columns of some data frame. So how could we use an apply function to improve this code? So we're applying the same function to every element of a data, or every column of a data frame. And so we could replace that with an lapply. In R, internally, a data frame is just a list. So we can use lapply to apply a function to each column of the data frame. And this does the same thing that this does while dramatically reducing the amount of code duplication we have. And so as I was describing earlier, these apply functions are the place where we would most likely want to use anonymous functions because we might just be doing something very simple and kind of one-off, or where we might not use this same function later on, but we just need a function that we can pass to a function like lapply. Lastly, I have one more quick note on this ... argument. Another thing that we can do with this ... is rather than passing these arguments along to some other function, we can actually turn them into a list and operate on them as a list. So suppose I wanted to write an impute NA function where I could give it any number of vectors and impute on each of these vectors separately. I can do that by rewriting impute NA to take any number of arguments with this ... So the way that I do that is I'm going to write a function, impute NAs, that just takes this ... argument. In the body, I'm going to pass the ... to the list constructor. I'm going to call it dots. So now dots is just a list of all of the arguments passed. Then I'm just going to use lapply on that list and do the if-else thing that I was doing in all of the previous versions. So that means I can pass multiple vectors into impute NAs and do the imputation on each of those vectors independently. Right, so that brings us to the end of functions and functional programming. We have about 20 minutes left, so I'm going to try to cover a little bit of the object-oriented programming material. If you have any questions on the functions part, go ahead and ask those now. All right, so for object-oriented programming, because we only have 20 minutes, I'm going to skip some of this. All right. So start off with object-oriented programming in R. Let's start off with an object that you already know. or a class that you already know, a data frame. So when you have a data frame in R, I can apply a function to it like head, and that prints the first 6 lines of it. If I look at the type of this data frame, it's actually a list. I can look at the attributes, and I can see it has this one attribute called class, and this happens to be a data frame. So data frames, though, they print differently than lists, and that's because of that class attribute. And so that means when I apply the plot function to cars versus a formula, plot does something different. So for example, if I go, so cars, I have this data frame of speed for cars. If I apply plot to this, I get a plot of distance versus speed. I could call plot in a different way on these 2 variables directly. And that gives me the same plot, but now my axis labels are different. And another way I could do this is to call plot on a formula. And that again gives me the same plot with the original axis labels. So I've called plot in 3 different ways. And plot is actually, even though I get the same plot, plot is doing something slightly different in each of these different situations because I'm passing a different kind of object to it. The first, I'm passing a data frame. The second, I'm passing 2 numeric vectors. And in the third case, I'm passing a formula. And if you were to think about how you might write a plot function that can handle all of those different situations, naively, it might seem like a bunch of if and else if statements, but that's not what's going on. Instead, plot can actually be specialized to whatever kind of object is passed to it using what we call object-oriented programming. So the basic idea of object-oriented programming is this is a way of organizing code around commonly reused data classes and methods. A class is just a blueprint for the way that we organize data. So for example, a data frame is a kind of class for heterogeneous tabular data. By heterogeneous, I mean each of the columns of a data frame can be of a different data type. So a data frame is a class because it's a blueprint for one way that we might organize our data. An object is an instance of a class. So for example, base R datasets comes with a data frame called iris, cars, empty cars. So these are all different instances of the data frame class. These are all objects. Inheritance is another part of object-oriented programming. And inheritance means that we can define subclasses that specialize their parent classes or superclasses. So if you've used any packages from the tidyverse like dplyr or even ggplot2, for example, let me load ggplot2. The tidyverse has its own version of a data frame called a tibble. So here, for example, is this miles per gallon data set from the ggplot2 package. And a tibble is a data frame, but it prints out a little bit differently than a data frame. And a tibble is a special kind of data frame, and it is a subclass of data frame, and it inherits most of its behavior from the base R data frame class. But it's a special kind of data frame, so it's able to specialize and behave differently in certain situations. And finally, a method is a function associated with some kind of behavior that is specialized to a particular class. And in R, we define methods based on what we call generic functions. This works a little bit differently than in other object-oriented programming languages, in that methods belong to generic functions. We saw one generic function in plot. So the behavior of the plot generic function will change depending on what kind of object is being passed to plot. So we have a plot method for data frames, a plot method for formulas, and so on and so forth. The plot is a generic function, and its behavior can be specialized by defining methods of plot for different kinds of classes. So as a simple example that I'm going to show you to kind of demonstrate this object-oriented programming idea, consider a simple pet simulator game. So suppose you're writing a game that involves some kind of pets. It might consist of the following elements. You might have an animal class that defines behaviors for animals generally. And the animal class might have child classes or subclasses called cat and dog, where cat and dog are particular kinds of animals. You might have a generic function called speak. So you might expect different kinds of objects to be able to speak, but they might speak in different ways. So that means you would have a speak method for cats and dog classes, but cats and dogs would speak differently. Then you might have an object named Mittens, that's a particular instance of the cat class, an object named Duke, that's a particular instance of the dog class. And if we called our speak generic function on Mittens, who happens to be a cat, it would call the speak method for cats, and Mittens would say meow. If we called the speak generic function on Duke, who happens to be a dog, we would get the speak method for dogs, and Duke would say woof. So I'm going to show you how to implement this kind of simple outline of this pet simulator game in object-oriented programming. So one quick kind of caveat is that this object-oriented programming in R works a little bit differently than in some other languages. So if you've seen code, especially object-oriented code from languages like C++ or Java or Python, in those languages, methods belong to classes. So the way that you would call methods in Python or Java or C++ is the name of the object dot the name of the method. And the methods are defined as belonging to the class. In R, we take a slightly different approach because R is what's called a functional programming language. So the focus is on functions rather than on the objects. And so methods in R belong to generic functions. And we call them just like we would functions. So when we call a generic function like speak, we call it just like we would any kind of function and call it on the object rather than doing it the other way around. Question is object-oriented programming implemented via the environment precedents you discussed earlier? No. There's two kinds of object-oriented programming in R, S3 and S4. Neither of these rely on environments, at least as far as developers go. If you're implementing a class in R, it doesn't heavily use environments. I'm not sure if method dispatch for S4 does somewhere internally. It might, but generally speaking, this doesn't rely on environments. There is another kind of object-oriented system in R called reference classes that actually do rely on environments. And the reason for that, the reason that S3 and S4 classes don't, while reference classes do, is another difference between the R approach to object-oriented programming versus something like Python or Java, is that R again takes this functional approach in that objects in R are always immutable. So whenever I call a function or a method on an object, that object isn't going to change. If that function tries to change that object, it's actually going to change an internal copy of that object. In R, objects do not have any internal state that might change. They're immutable. Whereas objects in C++, Java, and Python have internal state, and calling methods on them will change that object, and any other references to that same object will also be changed and updated. Whilst in R, whenever we call a function on some object, if it changes it, it'll always change a copy of that object and return a copy of it. And R takes that approach because it often makes reasoning about data a little bit easier. And so that's why reference classes are kind of an alternative way of doing object-oriented programming in R that is more similar to the Python, C++, Java approach, because they do have state. They allow objects to be mutable and have this mutable state. And they use environments in order to do that. S3 and S4 don't. They behave like ordinary R objects. They won't suddenly change if you pass them to a function. So generally speaking, most object-oriented programming in R is with S3 and S4 rather than with reference classes, because these reference classes that use environments kind of break a fundamental assumption about how data works in R. So as for these S3 and S4 classes, these are kind of two different approaches to object-oriented programming in R. S3 classes are things like data frames. They're a very simple class system. They don't have any formal class definitions. And the methods are what are called single dispatch. So the methods are only able to specialize on the first argument. S3 classes are very simple. They're kind of similar to the classes from Python if you use Python, except for the fact that they're immutable. S4 classes are a more complex class system. Objects or classes in S4 have a formal class definition so that there is a formal idea of what that class actually looks like. It has different slots, it has a specific data structure associated with it, and the different parts of the objects have to be of particular data types. S4 classes also have multiple dispatch, which means the methods are specialized on multiple arguments. When to use which? Most of the packages in base R and on CRAN use S3, which are pretty simple without complex dependencies. So these are simple classes such as things returned by LM, GLM. So these are simple data structures usually, and S3 is adequate for them. The places you will see S4 are places like bioconductor. In bioconductor, we are handling things like genomics experiments, proteomics, lipidomics experiments, all kinds of omics. And these are complex experiments with complex data structures. And so packages on bioconductor will use S4 classes in order to capture that complexity and be able to check whether an experimental object is valid for that class of experiment and actually makes sense. So because we're running out of time, I'm going to skip S3 and talk about S4, because in proteomics, working with mass spectrometry, we're mostly going to be working with bioconductor packages, things like the MSN-based package, Cardinal, and so forth. And these all make use of bioconductor data structures and the S4 class system. So I'm going to go ahead and skip ahead to S4. The S3 stuff is there if you want to look at it. S3 is much simpler, so hopefully S3 won't be too confusing if you want to go back and look at that. But S4, this is a class system that works the same way as S3 from a user perspective, but what S4 lets us do is it gives us a formality and rigor to the classes that we create. S4 classes have a formal definition, so we have to formally define what a class looks like. An S4 class has what we call slots, and these slots each have to be a specific data type. And we define what those slots are named and what data types are allowed to be in them when we define the class. Inheritance is formally defined, talked about multiple dispatch, and most importantly, with S4 classes is we can always check, we can define what a valid object of this class looks like, and we can check whether this is a valid object of this class or not. This question on what does dispatch mean in this context? So dispatch is how a method or how a generic function decides which method to call. So for example, plot is an S3 generic function. So we can define methods for plot for different kinds of objects. So there is, for example, a plot method that is specialized for data frames, a plot method that is specialized for formulas, and a default plot method, and so forth. Dispatch is how R decides which of those methods actually gets called when we just call plot on some kind of object. Single dispatch means that that can only happen on the first argument that we supply to plot. So here, if I provide speed, distance and speed, and then a second argument, data equals cars, the method is decided solely by this first argument to plot. It's only going to use the formula, or it's only going to use the fact that the first argument is a formula. However, S4 multiple dispatch means that we can define methods on different combinations of different of objects of different classes, which isn't always which isn't always necessary, but it is some additional flexibility. But dispatch just means how the specific method is matched with the generic function. So you can see there's a bunch of different versions of plot, and dispatch means how plot decides which one of these specialized functions to call as the method. All right, so if you've used bioconductor at all, there are some S4 classes you already know. So for example, summarized experiment is an S4 class in bioconductor for storing bioinformatics experiments. MSN sets and MSN experiments from the MSN base package are another S4 class. Delayed arrays are a class from the delayed array package on bioconductor for working with really large matrices and arrays. Bioconductor defines its own S4 version of a data frame that's a little bit more flexible in what it can store. So what does defining an S4 class actually look like? So an S4 class is formally defined with a call to set class. We give the name of the class. I'm going to say animal is a virtual class. A virtual class means that we aren't going to make objects that are just an animal, because an animal is too vague. So virtual means we can't create objects of that class, but we can create objects of its subclasses. So we actually want to create objects that are cats or dogs. We don't want to create an object that's just an animal. We can define what slots a class has. So these are the different members, the different data members that belong to this class. So we have a name that's just going to be a character. We want this to be a string. We can define a validity function. So this function will be called to check if this is a valid animal object. We're just going to check if the name of this animal is a length 1 string. Then we're going to define child classes called cat and dog that inherit from animal. I'm going to run this very quickly because we just have a couple of minutes left. I'm going to create a constructor for these. So these are just functions that return new instances of my S4 class. Internally, we do that using this new function. You generally don't want to have users call new directly, which is why we're creating these constructor functions. So if I run these, I formally define my animal class, create constructors, and all these do is these call this new function, which create a new object of that class. And then whatever arguments we pass to it are these slots. And I'm going to create a new cat called Mittens and a new dog called Duke. And the first thing that we typically want to do when we create a new class is define what it does when it gets printed out at the console. So in S3, we do that with a print method. In S4, we're going to do that using a show method. To define a method in S4, we use the set method function. We're going to define a show method with it, which is just the function that gets called when we print an object at the console. This is the show method for an animal. And this is just going to print out the name and class of the animal. So if I define this method, now when I print an animal, it says this is a cat named Mittens or this is a dog named Duke. I'm going to define a new S4 generic function using this set generic function. So this creates a new generic function called speak. So now I can define methods on speak. And I'm going to define methods on speak again using this set method function. So that cats say meow, dogs say woof. And now if I create a cat and dog named Mittens and Duke, and I ask them to speak, Mittens says meow, and Duke the dog says woof. So that was just a really quick rundown because we're out of time on what this example is trying to show of how we can formally define an S4 class using set class, create a constructors, define custom methods, define custom generic functions, and then call those on our objects. If you're interested in seeing a more realistic example of object-oriented programming in R and don't want to look at the source code of real-life packages, I've created a kind of simplified package that is relevant to working with mass spectra. So on GitHub, I have a link here to kind of an example, a very simple package for working with mass spectra in R. This is a very simple package that's for demonstration purposes only. And so this just shows examples of defining S4 classes for something like a mass spectrum. So this is a place to take a look if you want to see some additional examples. There's a final question. Can you define virtual methods in S4? No, we can only have virtual classes. Virtual methods are kind of something specific to C++. If you mean something besides what is implied by a virtual method in C++, then you'd have to tell me specifically. But there's no such thing as virtual methods in R. There are virtual classes, which are classes that can't be instantiated. You can only create instances of their subclasses. So that wraps it up for this kind of crash course to intermediate R. I know we didn't get through all of the material. That was kind of expected. Again, if you want to check out the rest of the material, it is all posted. There are links to both the GitHub of all of these slides on the Google Docs. And there's also links directly to the PDFs of the slides. And you can also check out this MS example package if you want to see a more realistic example of using an S4 class and defining methods on it. I'll hang out for a few more minutes if there's any additional questions. But otherwise, thank you everyone for tuning in.
Okay, thank you, Kelly. It's really a great course. It's so useful. I also learned something from it. And thank you everyone for attending the online May Institute course. I hope you found it useful. This Thursday, Kelly will give another lecture, which actually focuses on using the principles we learned today to develop the R package software for mass spectrometry experiments. And also Lauren Gatto, who is the author of MSN Base. Kelly just mentioned the package, which define a S4 class. called MS-NSAT. Many R package, bioconductor package, use MS-NSAT based on it. So Lauren will also talk about MS-NBase in his lecture. So we invite you to participate in the Thursday class, which is from 1 p.m. to 2 p.m. I think. So also, one thing I forgot to mention is the class today, we already recorded, and the recorded video will be uploaded to our May Institute YouTube channel shortly, I think in 2 hours after the class. If you want to review all the course material and the code that Kylie tapped today, you can go to our May Institute YouTube channel to look at it. Okay, thank you.
Thank you, everyone.